from Mathewson. I'm from Edmonton, Canada, where the average temperature is like minus the degrees it is right now. So instead of plus 32, it's minus 32. So this is very hot, and it was a bad choice for me to wear jeans today. Today I'm going to talk about AI and machine learning in the browser. Hopefully it interests some of you, even if you're not JavaScript developers. I can show you the applications and how machine learning in JavaScript happens. You can find me on Twitter at Keyfer or find me on GitHub at github.com/Keyfer. So I'm going to talk today about, first, what is AI, what is machine learning, what is neural networks, so we can just have a ground foundational level of understanding. So AI is the science of getting computers to perform human tasks. And these tasks can be anything from searching and planning. AlphaGo did this quite recently, a few years ago. There's a team out of the University of Alberta in Canada which is doing this with poker, Texas Hold'em right now. So this searching and planning, we can also do robotics, which is Boston Dynamics is doing this out of, I believe, MIT in the States. So these human tasks can be, the goal is that these can be accomplished by robotics, or by machines. Machine learning is an approach to achieve AI through a system that can learn from these experiences and data. So we feed in data to these neural networks, these machines, and then from this data, we hope that the machine can garner patterns, and then from that can predict future values. We're going to focus on supervised machine learning. There's two main types of machine learning. One is supervised machine learning, and one is unsupervised machine learning. Supervised machine learning is when the data we give our models are labeled. So if I was to describe this water bottle, I would describe it as maybe transparent. A Boolean has a cap. Right now it doesn't have a cap, but if we just say, yes, it does have a cap, and it has a label, and maybe it's 50% full. So those are all features I would describe this water bottle as, and the label I would give that is a water bottle. So with supervised machine learning, we give the model the answer for what the question is. So if the question is what is transparent, what has some water, what has a cap, the answer in supervised machine learning is water bottle. In unsupervised machine learning, we don't give an answer. So we hope that the computer can organize the data in such a way that it might not know what it is, but it can predict and gather relatives of that data. So, but we're going to focus on supervised machine learning. That's just an introduction into the different types. A big part of supervised machine learning is deep learning. And deep learning is a technique to implement machine learning through structures called neural networks. And this little diagram is what a neural network might look like at its really basic form. And we structure this after the neural networks in our own head, where we have an input stimulus, so be it the sound of my voice or the presentation you're seeing, and we pass that information through these input neurons, this input layer, through maybe one layer of hidden neurons or a number of layers of hidden neurons. And each of these neurons on this board has a different weighting to the overall importance. So the goal is that we give a stimulus and we get an answer. So if I give the stimulus, if you see this, that's your input stimulus, and the answer in your head, the output, is a water bottle. So we pass this stimulus in through the input neurons, which are weighted differently, because that could be a different type of water bottle. It could be a pop, depending on the color of the liquid. So that could be a difference of an importance. And we pass that through a number of layers to an output. So, as I said, deep learning can drive machine learning, which can then enable artificial intelligence. So these are how these three technologies work in harmony with each other. So they're often thrown around in kind of a bunch of different ways. If you read like TechCrunch or Medium, there's some confusion with what each of these different means. So it's really important to understand that there's different ways of achieving each of these different methods. The main goal of machine learning, not of all AI, but of machine learning in general, is prediction or inference. Given that we give our model a bunch of data, the goal is that it can find patterns in this data and can predict future values for unlabeled data. So given that our machine knows what 8 million water bottles look like, given that it can look at this, it can probably, hopefully, the goal of it is to decide that that is, in fact, a water bottle. Within machine learning, there's two main types of models. These two main types of models on the left are regression. So this is a simple linear algebra, y equals mx plus b, where we find the slope, the line of best fit. And on the right is classification. And classification is, again, pretty simple at its base. Is this a cat? Is this a dog? Or and that's a yes or no, but we can also classify between things. So I can say, is this a cat or a dog? So depending how we build these models, they might not sound quite different to us, but our machines are really keen to the differences in what we're trying to teach it. So another really important thing to note is that on our left, the difference between that line of best fit and each individual data point is what we call loss. It's just how wrong were we on our line of best fit compared to every data point. And that's an important distinction in mathematics and linear algebra, but also in machine learning. Because the goal for regression modeling is that we want to reduce loss at every point we can. Of course, that's impossible. There's always going to be outliers, and we're never going to be able to hit all the different data points on that. But the goal is that our machine can teach itself to reduce the loss and that it can adjust for the loss. So there's two. The main difference maybe is more clearly illustrated in traditional programming versus machine learning programming up above. So on our left is maybe more of a traditional programming model, where let's say we want to decide if an email is spam or not. Let's say a feature, let's say example is going to be an email, and feature is going to be the subject line of the email. So what we might have is we might have this if-else-if ad infinitum loop, where we decide whether, where we check if the subject of the email equals maybe foo, and then if it does, we label it as accordingly. Or we might check if it's bar, or we might check if it's foo bar, and this can go on forever, right? We never can truly account for all the different subject lines a human might send another human in an email. So at the very end of this list, we have this catch-all, and we kind of just say that we haven't really accounted for this yet. We might not know what it is, but at the very end, we don't really care because we don't know, so we're going to just apply this generic label to it, which is how spam gets in your email box still, even though we have this filtering. And again, this can go on for thousands and thousands of lines of code because we can never predict the value. We can only check an absolute value. Machine learning programming is quite different in the fact that this isn't real, there's no language called machine learning and that's how you write it, that'd be too easy. But the idea is that we predict a label for an example. So given an email, we predict the label for it. We change ourselves to reduce the errors or reduce the loss we saw on the previous slide, the difference between the line of best fit. And then we try again. And we repeat that process as much as we can so that our loss gets as small as it can be. So why should we care? Machine learning, this is maybe less specific to the developers at this conference. Myself, I'm developing quite a different number of languages, but I mainly focus on JavaScript. So as JavaScript developers, mainly, why should we care, as machine learning is, at its core has always been more of a high-level programming language such as Python? Well, you can apply theoretical parts of machine learning in any language. And this is a really key, amazing thing, is that we can take these high-level concepts of machine learning, such as regression and classification, or if you know nearest neighbor organization, we can take these high-level concepts and we can apply them in any language. And the cool thing is JavaScript has 4 million developers, and Python has 400,000 developers. So if we can harness the community that JavaScript and maybe a front-end development team would across the world, we can do a lot cooler and more interesting things a lot faster. Those numbers are pulled from LinkedIn, so maybe if you trust that source, I don't 100%, but it's 4 million is the number of people who added JavaScript to their skills, and 400,000 is the number of people who added Python or machine learning to their skills. JavaScript is also the most popular language on GitHub. So in 2017, JavaScript had the same number of PRs as Java, Python, and Go combined. If you just let that sink in for a while, that's a really crazy metric in that there's a lot more of us writing a lot more code, which is incredible, which is another reason that we can do amazing things in JavaScript. The most important thing is that we, as JavaScript developers, and maybe front-end developers, or as developers in general working for merchants or users, is that we have a really, really close connection, almost the closest connection to the users on the other side of the screen. And this is where we can bring into play interactive machine learning, where we can directly connect with our users and gather real-time data, which we can train these models on the fly, and directly impact how the user interacts with our app or our website or anything in real time, which is really, really important and crazy, and it's really cool, and I can't wait to show you some examples. So, a little side note is this is the growth over the past 8 years of machine learning JavaScript frameworks. So in early 2010, there was one main JavaScript framework for machine learning, and it was an early stage of something called brain.js. And what it did was it used the CPU, or rather the GPU, on your computer to run linear algebra. And this way we could run pretty complex equations, predictions, but it was still, graphics card at that point weren't really super powerful compared to what we have now, as well as the community around machine learning discoveries, exploration in the field wasn't as great as it is now. As of May of this year, we have 8+ frameworks. We have frameworks being developed by companies such as Google and TensorFlow, which have huge followings and a huge number of developers working to increase and better these frameworks. The first one we're going to take a look at is the newest version of Brain.js. Brain.js is an open source library of 2 types of neural networks. We talked about neural networks as an implementation of deep learning earlier. So the 2 types of neural networks that Brain.js covers are feed-forward neural networks, where you have an input stimulus, passing it forward through a number of hidden layers, out to an output stimulus to get an answer. And the second version that it covers is a little bit more of an interesting and harder to understand type of neural network called a recurrent neural network. And this is more so what our brains are. So as you hear me talk in this presentation, you understand each word I say based off of your understanding of every previous word. So your understanding of the talk at a whole is a culmination of your understanding of each slide I gave. It makes much more sense in a movie scenario where an hour and a half into the movie, the scene you see, you understand the plot and the character development and everything as a culmination of all the previous scenes you've seen. And this is how our brains work. Every time we see a soccer ball, we don't relearn what soccer or a soccer ball is. We understand that we've watched soccer in the past, or we've played soccer in the past, and maybe how we can pump a soccer ball full of air and how that impacts everything. That's a recurrent neural network. Brain.js is really cool because it's incredibly easy to get started on training these models on data inference, on prediction. There's 2 main points about Brain.js that I wanted to talk about. One is data is organized in an object containing an input and an output. And these are the features and the labels. So I talked about this at the beginning. The features of this water bottle are the transparency, are the Boolean if it has a lid or not, maybe a 0 to 1 value of how much water it has. And then the label is that it's a water bottle. Secondly, input has to be an array of objects, an array or object of values between 0 and 1. So we have to translate our data before we pass it into Brain.js. And that doesn't mean that our data we give it has to be between 0s and 1s, so I can't give it English or whatnot. But before we pass it to Brain.js, we just have to translate our data. It'd be no different if Brain.js only understood Italian versus English, and we just had to translate it before. But translating to this is a lot easier than translating our data to Italian. So this is a look at some of the training data we might give Brain.js, where we, at the top, we could have some training data, which is just an array of 0s or 1s, maybe Boolean values, 0, 1s, to describe anything, really. So maybe this 0 is that it's not opaque, 1 is that it has a lid, and 0 is that it's not full. But that's not really true because we have a measurement of liquid inside of here. The other training data might be used how we describe a color. So let's say our input data was RGB, and we described our data inside of RGB as 0.5. So let's say for red, we're halfway between 0 and 255, or 0 and 1. Green, the same thing, and blue, the same thing. So our input is RGB 0.5. Our output is gray. Gray equals 1. So we're giving our model features for the data, which is the red, green, and blue values, and we're labeling that piece of data as gray. What I was talking about was encoding or translating our data. Let's just say we needed to encode or translate that data before we pass it in, and we're using non-actual numeric values. So if we wanted to encode or train our data on ABC123 for whatever reason as part of this bigger training data, we can encode that data using that function at the top, where we're just mapping over every character, and for every character, we're dividing its character code by the total number of characters to get a decimal point for that character. All we're doing is just translating this into a decimal point value of its ASCII character code. And then we encode ABC123 into that character code value below and pass that into Brain.js. And that way it can read what we're passing it. So this is that exact same thing, but we're actually building a neural network here. This is the amount of code it takes to build a neural network with Brain.js, and this is how easy it is to get started. So at the very top, I hope you can all see this. At the very top, we're just requiring Brain.js. And then let's say we wanted to detect cats versus humans in our code, given a training data. This is obviously really easy, but it just goes to show the quickness that you can kind of train these networks. So we instantiate a new neural network, and then we give it training data. And again, the training data we give it doesn't have to be translated beforehand. We can have our training data in any way we want to and translate it as we pass it in. So in here, we're just giving a number of pieces of training data, inputs and outputs. The first one is height 23 kilograms, centimeters. Weight is 4 kilograms, tail is 1. So these are features for this data we're giving it. And again, that's repeated twice. Height 19 centimeters, weight 8 kilograms, tail 1. So we're saying that these two pieces of data with these features are cats. And the next two pieces of data we're giving it are height 160, weight 60, tail 0. And these two pieces of data we're giving it next are going to be humans. So our model is learning what a cat might look like and what a human might look like. It's important to know that with machine learning models, they don't know what they don't know. So if we tested our data, our machine learning model, against, let's say, the measurements of an elephant, it would only know the existence of cats or humans. So it's important that we train our models with enough data that they can understand all the different types of labels that we might want to gather from it. So we have our training data, and now we have our testing data. Let's say our testing data is a height of 20 centimeters, a weight of 6 kilograms, and a tail of 1. We don't have an output for this. We don't have a label for this data because this is the data we want our model to learn how to predict. At the bottom, we encode and process or translate our data before we pass it into this neural network. So that's on our right-hand side, where we're doing the same thing, where we're mapping over every character in that object. We're translating it to a number between 0 and 1 based off its ASCII character code. And then, again, we're encoding that in the processing training data. Back on the left, we can see that all we need to do to train our model on this data is call our neural network, which in this case is called cat detector, .train, and we pass it our process training data. Then what we can do is we can call catdetector.run on our process testing data. And the output, it's a little bit hard to see here, but the output is an object with 2 keys, and the value of which the model predicts that data belongs to. So this data that we passed it, the model is 93% sure that it's a cat. It's 7% sure that it's a human, so we are more likely dealing with a cat here. Of course, the data we're giving it is pretty drastically in one direction, right? We're not super close, with our testing data, we're not super close to a measurement that a human could achieve. So the more testing data, or the more training data we have, the more minute details we can include in our testing data. We can also call brain.likely with our test data and our neural network, and we can just get a simple value back. In this case, it gives back cat because that's the highest likely answer here. The second neural network, or second machine learning framework I want to talk about is maybe a more popular one, called TensorFlow.js. So TensorFlow.js used to be called DeepLearn.js before Google I/O this year. And DeepLearn.js was an open source framework developed by Nikhil and Dimitri from Google. I don't know their last names, or I can't pronounce them well, so I'm not going to even try. But they both work at Google now on the TensorFlow.js team. And TensorFlow.js is built off of the TensorFlow Python framework, which is an amazing feat that we can try and rebuild this in JavaScript. And it's a general purpose machine learning with hardware acceleration. So what does that mean? So that means we can do things like natural language processing. That means we can do regression, object classification, generative art. It can do a number of different machine learning techniques and implementations. Data, in this case, has to be fed as tensors, which is a data structure which represents an n-dimensional array, as opposed to the last one, which we needed to pass in just a simple array. Imagine you had an image that was, say, 30 pixels by 30 pixels, and for each pixel in that image, you had an array of values, say an RGBA. So you're trying to group all that, and we call that a tensor. So on a 30 by 30, you might have 900 or 9,000, I'm not too sure, I forget on the top of my head, whatever dimensional array, each inside of it with values for that pixel. And then we feed that as tensors to TensorFlow. This is called Teachable Machine, and this is something Google launched early last year, which is a neural network that we're training inside of our browser. So here I've trained this neural network to tell the difference between when I'm holding up a pack of mints and when I'm holding up a pack of Post-it notes, and depending on what I'm holding up, present a GIF of what I'm holding up. And I'm doing that by training two different classes, the green class and the purple class. And each of these classes represents a grouping of images and a grouping of data. I can increase the number of classes, so there's an orange class that I just didn't train. And this confidence bar that you see shift from the green confidence to the purple confidence is the confidence that the machine is showing you the right image, that the image currently on the webcam is part of the class you were training. And this is all done using TensorFlow and maybe 100 lines of JavaScript, which is really, really cool. And we're going to go through that code right now. So this is pretty much that whole thing is running off this amount of code. I realize it's super hard to see, so I've broken it up a little bit. What that is a k-nearest neighbor image classifier. I'm not too sure how many are you familiar with k-nearest neighbor, but what it is a way to classify images based off of the almost a democratic vote of an n number of nearest neighbors. So let's say I have 100 pieces of data, and I'm trying to test against a certain data point. Well, let's put my data point in that maybe neighborhood, and I compare my data to the 10 closest neighbors of that data, and based off of what all they say that this data is, I can classify my data as the result of that. So this is, I import k-nearest neighbor image classifier from DeepLearn, now TensorFlow, and I import all of DeepLearn itself. I set the number of classes I want to train. So here I'm training 3 different classes, a green, a purple, and an orange. I could have just removed the orange here, but you can train any number of classes. This is really cool for compass directions, so northwest, south, and east. I could have trained this data to recognize when my face is turning up, down, left, and right to represent a direction on the screen, and I would have 4 classes there. So classes can be increased to any number. I'm also setting a number for my top k value. That top k value is the number of neighbors I want to look at to classify my current data. And the bigger the number of neighbors, the slower your process will be because the comparison is higher, but the more accurate your data will be. Next, I'm setting up my setting up my main constructor, which is I'm setting training to -1. So when I load the screen, I'm not going to start training immediately. And I'm creating a new k-nearest neighbor neural network or classifier with those constants that I just had made. I can then set up my webcam feed here using Navigator, and then create event listeners for the buttons. We all know how to do this. You can do this in HTML. You can do this in JavaScript. That's not the most integral part of this. But what is really important is that what we do now is we create a set timeout function that runs every second if you want it to be super slow, every 100 milliseconds if you want it to be pretty quick. Again, the faster you do this, the more resources this is going to use. And what we do is on the webcam we've created, we call request animation frame with animate as our callback. And what does animate do? Well, animate is kind of the chunk of the work of this k-nearest neighbor classifier. So what it does is if the video is playing, we get the pixels, that n-dimensional array, each with an array of RGBA values, and we convert that to a tensor using the function from pixels that DeepLearn or TensorFlow gives us. We can then get an example count of the number of examples we've trained so far, which I'll talk about a little bit later. We then say if this is training, which is if this dot training doesn't equal -1, meaning that we've, on our event listeners, we would have subscribed this dot training to the class that we're currently training. But if this is currently training, we want to add an image, add the tensor data to each one of those classes, so that when I'm holding up the pack of Altoids and I want to train Altoids to the green class that we saw, I can call this.knn.addImage. If we want to train the purple or orange class, this handles the exact same thing based off of that event listener that we might have created. So what we're going to do is then, if we have any examples, if we've trained any of our classes with any data, we're going to run this k-nearest neighbor sort of prediction network, which is we predict the class of the image that we give it. So we get the from pixels, we get the data as a tensor, we pass it to the predict class, then we get a response. And that response we can console log, or we can do whatever we want. We can add CSS to it, we can add a class and then change that with CSS later. But what that response gives us is that the index for the class that it predicts is 0, and its confidence is 100%. So let's say I'm going to go back to this slide right here, is the confidence you can see is wavering a little bit and then becomes very confident depending on the webcam. So at each moment, every time that's firing, we can get a return, we can get a response, and then update the percentage if we want to show the user a real-time percentage of the confidences. We can also display a different GIF. We can do anything we want with that real-time data, which is really, really cool. Then we can dispose of the image if we're not currently training, and or if we have finished training, then dispose of that data. So we don't need to keep each frame that we capture unless we're training it, which is awesome. So this is all the code it takes after importing deep learn or TensorFlow to create this neural network classifier, which is a really important thing to know, is that how easy it is to do this on the browser. Because before, we used to have to serve these models from Python and pass them into maybe things like Dialogflow, where we would serve these from a server in the backend without having any input from the user. But what we're doing is saying that in real time, what I look like holding up my pack of Post-it notes might be different than everyone else. And instead of training and using my data on maybe a model that 300 people in a different country might have changed, I can use my real-time data that I'm training to predict maybe what I'm holding up or what direction I'm looking in, which is amazing, and I can show you some examples of things doing this. So I think we have a bit of time. I'm going to try to show you guys some of this stuff in real time. Hopefully you can see this. So the first is fast neural style transfer with deeplearn.js, now TensorFlow, where we can in real time train models based off of the style of a painting from a maybe famous artist, and show some really transfer the styles from their maybe type of paintwork or artistry and onto the pictures we're giving it. So let's say this face, we want to transfer the style of The Wreck of the Minotaur by JMW Turner. And what we can do is we can download and train these models using JavaScript, and we can run these models in the browser. Nothing's happening right now other than running those models and predicting what each pixel should look like given the style and given the input, which is down below. We can also do this on I don't know why all these. Okay, let's that one, and let's say we want to use the wave. So we can quickly apply the styles from any image to any image using only JavaScript and the models that we can train in the browser. This is another fun one, a pretty interactive one, called Cyborg Writer, where we've trained models, not me personally, but this team has trained models based off of the works of a number of different people, such as Shakespeare, Ayn Rand, science fiction, Wikipedia, US Supreme Court, Taylor Swift. I'm not going to use any of the more kind of ones that might get me into trouble, but let's use science fiction. And what we can do is we can, with the models that we've trained in the browser based off of hundreds and hundreds of words, thousands and thousands of words, we can get our model to predict or give us some sort of, if we hit writer's block, this might be able to give us a little bit of a boost. So let's just say, like, I am at shift conf, and this talk is going good. And then I can press tab, and this can start predicting what the next sentence is going to be based off of the work it's seen. In this case, it says, which was he lovely in the bottom of the other, which kind of proves that machine learning isn't going to take over the world really quickly, but we can also keep this going. I don't care anything to me, and I got time to find you, but I don't see when I had a, and it doesn't always make sense, but you can do some really cool things. You can turn up the weirdness value. So this might get pretty weird. Let's turn it all the way up and say, now this talk isn't going as great. Yeah, that doesn't make any sense. So the weirdness value really might mess with this. But this is a really cool program, all done using JavaScript to train models in the browser that's going to keep saying things I don't understand. This is another really cool one. So what this team has done on the TensorFire library, built off TensorFlow, is trained image classification in the browser. And hopefully this works. Cool. So I can begin to play rock, paper, scissors in the real time based off of image classification. And the wavelengths you see are the prediction, that percentage value of prediction that it's certain I'm holding up a certain thing. There's also a hand, a rock, and scissors, but then a baby at the top, and I'm not too sure what baby is in rock, paper, scissors, but I've won that one somehow. Scissors, okay, we've tied. So this uses image classification, the TensorFire library, and real-time pixel-by-pixel tensors to determine what I'm showing on screen. Another really cool one was something, I thought I had this open. My apologies, I'm going to open my presentation. I don't have that open. Okay, I'll show you one and then the other. This is something called Emoji Scavenger Hunt, which is developed by Google last year. The sound doesn't quite work, but what it's saying right now is that emojis are something that's really used a lot right now on mobile devices, and users are using this. And sometimes the distinction between what an emoji is and what the actual action or the object is has changed over time. So what Google set out to do was, okay, let's see if we can, using emojis, predict or get the user to show us what that emoji might look in real time. So this is an open source project using machine learning, the TensorFlow library, to, based off of a network of emojis, predict and have image classification. So what this is a website which a user walks around in a scavenger hunt and tries to find something that the phone is telling them about. It's a really cool system, all done in the browser using JavaScript for image classification, object classification, pixel-by-pixel generation, and as well as object prediction in the bottom right. You can see that as the user runs around, the Google is saying maybe that was a seat, maybe that was a watch. And it's a really cool tool. I encourage you all to use it. It's a really fun, interactive way to get started and seeing what machine learning can do in the browser. I also have time for one more, which is something I've been playing around with quite a bit, which is something that has really inspired me to learn this, which is called Webcam Pac-Man. What Webcam Pac-Man does is it sets up using TensorFlow.js, and it uses 4 classes. And I mentioned this, I hinted at this a bit earlier, but the classes are looking left, right, up, and down. And we can train our models to recognize only us and keep the data on our machine. We don't have to use anyone else's data. We can train the machine, so you can see here, to recognize up, down, left, and right, like a joystick in arcade. So what I'm going to do is I'm going to click and hold examples of me looking up, or maybe I'm going to point up, because that might be easier. So I'm going to click and hold. So I'm going to move my finger around to get a bunch of different kind of featured data, and that'll be the north example. I'm going to hold my direction left and train a bunch of data there. So you can see right under the pictures on the right-hand side of your screen, it's increasing the number of examples. I'm going to train it right. And I'm just moving around so that the model has different information to work on. Because if I stayed right here, only if I was right here, the model would recognize that I'm looking right. I'm also going to train down below. So like that. Perfect. And that should be good. We have over 100 models for each one. So I'm going to then train my model. I'm training this model in the browser, and what it's doing is it's reducing loss as much as it can. And it got the loss down based off all of our examples to 0.0001. And this is maybe the riskiest part, as I'm not too sure if this is going to work, but let's try it. So, OK, I'm going to hold left, and then up, left, oh, no, up, left, and then how did I do down? Oh, like that, and then I did that. So what I'm doing is I'm training, I've trained this program to only, and then it's very hard to win. What I've done, thanks. So I'm not too sure what, there it goes. So while this is really cool, and the fact that we can play maybe some side-scrolling or Pac-Man arcade games in our browser, there's something deeper behind this, which is that we have the chance, using machine learning, to develop some amazing things. We can use real-time data from a user, maybe that doesn't have use of their hands, or doesn't use a typical mouse and keyboard, to make the user be able to use the computer in a way they never thought how. So for a person who doesn't have the use of their fingers or hands like many of us do, we can train a model in their browser, all the data is safe with them, to recognize when the person can look up, down, left, and right. And we can make that available in a Chrome extension or as a program running on the computer so that their cursor could move up, down, left, and right. And maybe we could train their model to recognize that when they blink, what they mean to do is hit enter, or that click a button. And we can begin to create amazing accessibility options among many other things for users that might have not had the same accessibility that we have before. So this is just the start of it. You can do some really fun things. You can get up on stage and talk about playing Pac-Man. It's a dream I've always had. But you can also really impact the world and a lot of people. This was another project. I wish I could show you a demo right now. This is something I've been working on for the past 6 months, which is, has everyone heard of the TV show Westworld? I would assume, yeah, okay. Westworld is a TV show about kind of this like mildly dystopic future, but something they launched last year was this kind of robot you could talk to. And the humans in the show talk to robots that act and feel like humans, and quite often get kind of that uncanny valley gets forgotten about. So BritBot was a program I'm building with my brother, actually, and Sky TV. It was a contract we got, and it's an online chatbot built entirely in JavaScript, which is trained off of hundreds and hundreds of years of newspapers and books that you can communicate with in real time and interact with. I'm hoping this launches sometime next month. I'd be really excited if it did. And you can interact with voice, you can interact with video. The goal maybe future is for a webcam to start to learn how it can detect facial symbols of maybe sadness or happiness, and how that changes conversation flow. So that as you see me and maybe I look scared, my talk and the way you interpret me changes. Or if I look happy and boisterous, that the conversation we have is going to be a lot different. And my hope with this is that I can build a robot that I can talk to. I guess that's really sad. That's fine. What I want to say at the end of this, and what I hope you all take away from this, is that while this may seem silly and it may just all seem like it's for fun, there's some really amazing things that we can do as developers with machine learning. And it's very easy to get started, and it can really impact a lot of people. And you can play games in new ways, and you can help people who haven't been able to use computers in new ways, and you can play with computers and build robots and do all these sorts of amazing things. I work at Shopify. This has nothing to do with Shopify, this talk, but if you want to come work for us, we have offices in Canada, in the USA, in Berlin, in Vilnius. We also have remote jobs. If you want to talk about that or this, please come talk to me after the show. Thank you for coming and listening. My name is Keyfer Mathewson.